Hello. So today I'm going to record my first video where I'll be building a mini chat GPT that can speak Shakespeare language exactly how Karpathy did in his video. And the code is basically going to be the same, except I'm going to explain a few concepts and at the end modify the code a bit and then show you how to deploy it to a virtual machine that has a large GPU and A100. Also, I want to use this video. This is sort of going to launch a thread of videos in which I'm going to build foundational machine learning models from scratch, and build up all the modules from scratch, and use that to sort of work our way towards more advanced and then the latest cutting edge implementations of things. Eventually I want to build a multimodal image to text model, text to image model as well, like Stable Diffusion XL, Stable Diffusion XL3. So I want to build all these in scratch and do all the optimizations in scratch. And I'm going to start with this mini GPT model because I found it to be a great way to break into this and learn PyTorch. When you implement these foundational machine learning modules in PyTorch from scratch, personally, I don't think you really understand. Well, personally, I didn't understand what was happening until I implemented them from scratch. I'm also going to, as part of these series, I'm also going to be doing the math on my iPad, um, on screen and showing you how to derive the objective function and then coding the model. For right now, since this is sort of an MVP, a minimum viable product, this is my first video. Things aren't ideal. I'm in Thailand right now, and I'm in this room that actually I don't have internet. I have to use a hotspot on my phone. Fortunately, I have that. It's like 85 degrees in here because there's no AC. So I'm like constantly sweating. But it's all good. Um, I don't have a capture card to hook my iPad up to this OBS. So I won't be able to do the math until I get back to the States, and get that equipment, unless I can find it somewhere here. So I'll have to show you the math on deriving the autoregressive objective function in another video. So I think that's enough for the intro. So let's just get started on coding this model. Um, I'm going to do it all in Vim, which is an incredible tool if you don't know how to use Vim or Emacs. I don't know Emacs, but I know it's just as versatile. Some people, there's an Emacs camp and there's a Vim camp. My mentor used Vim, so I'm going to use Vim. If you're not using one of those, I highly suggest you learn how to use it. It definitely takes some time to get good at it, but once you do, there's no going back. I mean, the amount of, the speed at which you can type code is unparalleled. So anyway, so we're going to first I'm going to get the data. I'm going to use the same data that Karpathy used, the Shakespeare data. It's going to be a character level language model. So the individual characters will be tokens, and then I'm going to make sure that we can create a batch to feed to the model. Then we'll create a baseline model, which is just word embeddings fed through a fully connected layer that um, gives you logits over the vocabulary size, so every possible character. And then we're going to softmax that, and I'm going to make a generate function to generate data, just given like an index, passing in an index. And then I'll write a training loop, and then I will start adding successively to the model. And then at the end, I'll show you how to deploy to a run pod container, which is a virtual machine, that contains an A100, to train faster. And then I'll turn the character level model into a word level model, so word tokens, and see how that changes the generations. So yeah, let's get started. So import, let's just do some imports. Import torch, and then as nn. Import torch.nn.functional as f. Let's open up another. Okay, I already have the data, so I'll add a link in, I guess, the repo that I post, and also maybe on the video description how to download the data. But so first let's define this data classes. From data classes import. So I like data classes. I'm gonna create this data class called config and pass it around. Instead of defining a bunch of hyperparameters explicitly in the various modules that we'll be defining. Just for this video, I'll do this because I'm just kind of lazy and I don't want to have to write out the hyperparameters. I just want to pass around a config file that contains all these different parameters. But I think once we start implementing more and more modules, I'll have to define the parameters or the instance variables explicitly, just because it'll be a bit more intuitive. So context window size is going to be the number of tokens, the maximum number of tokens that we can pass in for training or for a generation. So if we're saying, what's the next token given, a history of tokens, then we'll say the history window size is of size 8. So given 8 tokens, what do you think the next token will be? So I think 8 is just a good toy number to work with for now. Batch size, let's say 4. Wait, I'm typing Java right now. So let's just leave that there for now. So we'll just we'll do most of the work in train test model, and then main we'll just call that method. So yeah, let's get the data with I need pathlib from pathlib import path. With path, I think it's there. Yeah. Dot open read text receives f.read. Let's run this. Get a quick baseline. Also, I'm using a Conda environment. I have a requirements file. It's just using Torch, NumPy, and NLTK. I'm pretty sure that's it. So if you want to follow along, you can just pip install -r using that conda environment. Python language. Oh, yeah, of course. It's running a different file. Python language modeling. Why is it? What? Oh, I'm thinking the model is generating something. Oh my goodness. Yes. So, okay. So we got Python language. Okay. So there's our text. So now we're going to create a vocabulary, so all characters. I'm going to create a data class to do things like return batch, estimate loss, stuff like that. So class data. Pass this config file around. It's gonna have get batch. Let's see. So then data. Probably gonna pass in the text because I want to create vocab in this data file. Maybe this isn't the most engineering fluid way of doing it, but for now it works. I like it. I just didn't want to do a complete, just one straightforward script. I like breaking things into modules and classes. So let's see. Text. So vocab receives list set text. And then ideally I wouldn't be setting vocab on the config file inside of the data constructor. It's kind of like hidden. It's best for readability to set this outside of the constructor, but that's okay. Vocab config.vocab size receives. Now I want to encode. Now I want to be able to encode a string of characters. So if you pass me So if we have a string of characters, I want to be able to turn each character into an index that we can use to look up a vector. So the index representation will be given by the encode function. So we'll have def encode. We'll pass in token. We'll get S for S in token. And then self string to int, which is the lookup, which will turn a single token into, tokens. Which will turn a single token into a integer. So string to int is dictionary, turns a character, chn enumerate vocab. And we need to decode as well. It's just the opposite. Boom. So, drink some coffee. So, okay, so let's see if there are any errors right now. Config is not defined. Okay, so now let's see if we can data.encode. Boom. All right, I trust that. So now let's work on getting a batch. So we want to, if we have a batch size of 4, we want to have four sequences of tokens stacked into a tensor. And then the first sequence will have, so it's context window size of 8. So you'll have 8 tokens, so 8 characters encoded into their integers. So you'll have 8 and then 8 and then 8 and then 8. So how are we going to do that? We're going to, first I need to define the data set. Self.data, data equals torch.tensor self.encode text. And then dtype torch.long, so make sure the data type is long. And then we need the train test split. So let's say train split. Let's make that a 9. This is a float. Int config data data from the beginning to end, from end to the beginning. Let's call this train data. Let's call this val data. Okay, and let's make these properties of the class. What else do we need? Okay, now let's work on getting a batch. I think we have everything we need. So get batch. If it's train, if we're doing this for training data, data receives self.train data else self.val data for, and then we need to make a torch dot, we need to make a tensor that contains the index, where one index is the starting point. It is an index into a chunk of data of size 8. So we've encoded out all of our text data, and then we can select a random index, boom, and then that plus 8 represents 8 tokens in a sequence. So we'll sample 4 of these starting points in the data. So torch.rand int from length of data minus config.cw size. So we don't want to sample past the size of the data minus 8, because if we do, then we're going to chunk outside of the data set and get out of bounds. So, and then we do this, and then we say config dot batch size. We'll shape it. It'll have this shape. Indexes. And then, so if I print IDX, right? Oh, wait, hold up. Data.get batch train config has no attribute batch size should have batch size should be 4. Boom, we have 4 starting indices, so we're going to add 8 to each of those and then stack them on top of each other. So let's get a list. Let's just say L is data index, so I to I plus self.cw size, so plus 8. So that's our sequence. That's one sequence right there. And then for I in the index, let's call this indexes. And then print L. So I should CW size up config. Boom. So now we have 4. Those are 4 data points that we're going to use for training or test or validation if we pass in validation as the value for split. Now we're just going to stack these in a tensor. Torch.stack. And it's going to be along the 0 dimension, which is default. So I don't have to actually specify the dimension. Boom, stacked in a tensor, great. And now let's do the Y. So this is autoaggressive language modeling, right? So, you know, this is, let's say this sentence is the cat, or sorry, let's just say we're doing word level. It's okay. So we're doing character level modeling. So let's take the word um, um, artist, ARTISTS. Okay, let's just say it's 7. Let's just start with, so A is, so if we feed an A, the label is going to be R. If we feed an AR, then the label is going to be T. If we feed an ART, then the label is going to be I, right? So it's autoaggressive language modeling. So this is all stuff. Ideally, if I had my iPad, I would show you exactly what I'm talking about beforehand, but I'm going to have to release that video next once I get my hands on my iPad, and then you can watch that first and then watch me code it. Or maybe I'll just redo the whole thing, but for now, this is going to have to do. So all we're going to do is take the next character in the sequence, so just +1, +1. And then we're going to do send both to device. We need to, if we're using a GPU, we need to send it to the GPU right there. Well, we don't need to right there, but it's easier if we just send it to the device right now. And then return XY. Boom. Okay, so now that we can get a batch of data, let's create our model. Let's create our model. Yeah, let's do that. Let's create our model. So class language model. Everything is, if you're using PyTorch, is gonna subclass and then dot module. Def. Let's create the constructor. We're gonna pass this config file around, and then we're going to always call super forward, and then we have to define the forward pass, right? Always. So whenever, you know, all of these classes are callable, which means they can be sort of treated as functions, and when you use the object, when you instantiate an object and then directly on the object you call it as a function, the forward is what's being called, and this is also what's called when you're training your model and you're doing a forward pass through the data. So if that doesn't make sense, you'll see what I mean when we actually use this class, right? So forward, let's just do pass for now. So language model, so we're gonna do a baseline right now. I'm not just gonna build a transformer right now and then just use the transformer. I'm gonna show you incrementally how these improvements can be made, and then show you how the loss can get better and better over time, as it gets hotter and hotter as the time moves on in Thailand. It's 11 a.m. right now. By the time it hits 1, this might take us a couple of hours. By the time it hits 1, I'm going to be sweating. Okay, but I can't turn my fan on because then you can't hear me. So, ay, ay, ay. All right. Okay. So, all right, the most naive model we can make is word embeddings, right? So we're going to map these integers, these character level integers, to embeddings in a lookup table. So, you know, C maps to integer 52 and 52 maps to vector or whatever. And they're going to be initialized with random parameters, right? So, you know, we're going to say that this embedding table has dimension of size n underscore embed, size d, right? So let's just say 32. So each character integer maps to a vector of size 32 initialized with random values. and then we're going to pass those values through our language model is just going to have a linear layer, and then we're going to perform cross entropy between the logits from that linear layer over vocab size and one hot encoding vectors represented by the next token, and then we're going to compute that loss and back propagate that loss over the network. That's how we're going to train our model. So it's just going to have an embedding lookup table with trainable parameters and a linear layer that outputs logits over the total vocab size. So I think the vocabulary size is 65. So let's implement that. So embedding token, embedding table is, we have this already. PyTorch already has this lookup table, this parameterized lookup table. And we're going to say the total possible, values you can use to look up will be vocab size, config.vocab size. And then it's going to return vectors of size, self config.n embed. So n embed, we're going to define it here. Okay, and then we're going to have language model head, which is going to be a linear layer, and it's going to take in size and embed, right? So we're going to look up, we're going to start with a character, then we're going to encode that character to an integer, then we're going to look up the corresponding vector in this embedding table. It's going to return a vector of size and embed. We're going to pass that vector to this linear model. And then we're going to do that as using batches. So it's all going to be vectorized using batches. And this is going to return logits over config.vocab size. So it's going to say, and then we're going to turn that logits, we're going to normalize that logits using softmax to get probabilities. And the highest probability, the character with the highest probability is going to be the prediction. So for now, I think that's our model. So forward pass will be self.token embedding table x. Actually, let's say inputs, targets, inputs, toke emb, and then self.language self toke emb. This gives us logits. And for now, let's return these logits. So model, language model. And then here, so we define our model here, and then it's callable, right? So this, and then what that means is if I treat this object like a function and I just call it, it calls the forward method we defined above, right? And I'm going to pass in the data, right? Because here we see that forward accepts inputs and targets. So get batch is going to be x y, right? That's what it returns based on what we defined above. And we're going to pass in inputs and targets. And right now we're not doing with anything with the targets in this function, but we're going to in a second. Let's just see if that gives us, actually let's just print, let's not even return, let's return none, let's just print logits. Full cap size, it should, because we should have language model, right? So we need to create the data object first, up there. Device is not defined. Of course, we need to define the device that PyTorch is going to be using. We'll just do that as a constant. Device equals CUDA if CUDA is available. We'll use the CPU, which will use CPU a lot. There's a lot you can do with the CPU in terms of just getting a model to work and seeing if your losses are tracking properly and seeing if you can just get a model to make general predictions. There's a ton you can do with just the CPU. And as you watch, as I make more videos and you watch how I do these things, you'll see what I mean by that. So boom, we got ourselves some logits. Okay, so now let's compute a loss. So loss is f.cross and entropy between logits and targets. But actually, before we do that, we need to reshape them, because cross entropy expects your it's going to compute the loss across the entire, we want it to compute the loss across the entire batch, so we need to flatten the batch and the token dimensions together. So we'll say logits receives logits.view. So first logits.shape. You're going to see me do this a lot in the coming videos. Is whenever I'm in the forward pass, I'm going to call shape and then just make these singular, these variables of singular letters that represent dimensions, and we're going to use those dimensions to manipulate tensors. It just makes things a lot easier. I really don't like making dimensions words unless I have to. I'll make them singular letters, and then in the comments I'll define what those letter means. I just personally think it's a lot cleaner. So B, and I typically stay away from uppercase unless, I don't know, just easier for me to type. So BT, D, which B, batch size, T, context window size, D, num dimensions of word, embeddings, B times T, -1. -1, if basically it allows, whenever you're calling view, it allows PyTorch to infer what the dimension should be. So if you have B times D, the remaining dimension has to be, B times T, the remaining dimension has to be D. And the way cross entropy works, you're gonna have to look a lot of these things up to yourself. You know what I mean? I'll explain them, but sometimes I might miss something. So as I did as well, I had to look things up. Like cross entropy, the way it works is it will create one hot encodings for your targets. So you'll shape targets equals targets dot view B times T, right? And it won't have a last dimension, but when you pass it to cross entropy, it will create one hot encoding vectors that it will compare against the logits, right? So Boom, 4.06. So I think the vocab size, oh, I need to set the seed because this fluctuated too much. Seed, same one Karpathy uses, torch.manual seed. So if we run this program twice, we should get the same loss, 4.59. I don't know. We're setting the seed anyways. Maybe there's other seeds I have to set, but that should be fine for now. But what I wanted to, so vocab size is 65. If you take the natural log of 65, you get 4.17. So this is the log odds. If you want to know like what a random, if your model is making predictions around random, you take the natural log of the number of classes. That'll give you the log odds, which will let you know what the loss, what a model that is making predictions at random, what its loss would be. If it's approximately around there, you know that your model is random. So this looks good. These look good. What did I want to do now? Okay. So I can do a forward pass. Now let's generate. Let's work on generating just so we know after we start training, we have something like a interpretable benchmark. Generate self index, so one starting index, max new tokens. And what we're going to pass in is in tensor zeros batch size 1, and then the next dimension 1 for representing, you know, one index of a character. So we're just passing in, we're conditioning the generation on one character, and we're saying, given that character, start generating another character, and then they take those 2 characters, generate one more, take those 3 characters, generate one more, take those 4 characters, generate one more, and so on until we say do that until max new tokens equals 1,000 by default. Torch.zeros dtype model.generate tensor out tensor, let's just print, and then the out tensor, the 0th value dot to list. That's going to contain what we want to decode. And then if we join all those characters that it decodes and print that, that's going to give us a printable value. But for right now, we just print tensor. So how are we going to do this decoding? Okay, so for in range max new tokens, right? So as long as we have more tokens to predict, we need to call the model, right? Self conditioned on some kind of index, get some kind of logits, and then a loss, which we don't care about. We're going to do a softmax. I'm just kind of doing a skeleton on this skeleton code. Softmax on the logits over the last dimension, right? Over the last dimension. So we'll have a logits for one, we'll have a logits for the next character, a distribution for the next character. We'll say, do the softmax on those logits, that'll give us probabilities. And we'll define a multinomial distribution based on those probabilities, which we'll sample from that one time. We'll say that's the next index. And that we'll have to concatenate. So we'll have a sequence of indexes starting with one, then we get a next, and then we concatenate that index to the sequence of indices. So torch.cat idx to idx next on the last dimension. We'll say that's the index. So and I'll explain this. So IDX, this is going to be the condition. IDX, now we're going to sample from, so everything in the batch, which is just going to be one, but if we wanted to pass more in the batch, we could. The context window size is 8, so we're going to, but let's say that we're generating it, it can be 1,000 tokens. So let's say in the iteration we're on number 100. We're not going to pass in 100. Our context window isn't that large. It's only of size 8. So we have to say everything in the batch dimension, but then from negative config dot context window size to the end. And then we don't self.config equals config. And then we pass, so this will be our I think maximum of 7 tokens. Sorry, maximum of 8 tokens. And then we'll pass that in here and get a prediction over we'll get a prediction for each, right? So given the first, we'll get a prediction for the next. Given the next 2, we'll get a prediction for the next 3 next. But we don't care about those first 7. We only want the last one, which is why we do this. We select everything in the batch, then only the last token, only the logits for the last token, and then all those dimensions of the logits, right? And that's what we compute our probability distribution over and sample from here. So this should work. So yeah, let's see what happens if I run this. Oh, right. So I'm not passing in any targets here where it's expected. So let's make this optional. But if this is optional, then if targets is none, that means we're doing a generation. That means we're not going to compute any losses. So if targets is none, so targets is not none, we're going to do all this, else we'll just say loss equals none. Okay, so we have an out tensor that should be of size max new tokens, which is 1,000 by default. And that will be our language generation. So we'll decode that, and then that should actually give us language. It's not going to make any sense because the model isn't trained, but it should still be something. Boom. Okay. So now we're going to start training our model. So let's make a training loop. Okay. For boom and range, so for iter in range, config.max iters. This is where we're actually going to estimate the loss. We'll do that next, but for right now, we will so we define our, well, let's just yank this line of code. Let's yank, well, let's see, yank this. And then let's put this generate at the bottom, outside the loop. So we'll actually put that here, and then we'll put this here. So this is mini batch. This is essentially mini batch gradient descent. Well, I mean, this is basically optimizing per mini batch. So we're computing the loss per mini batch. So optimizer torch.optim, let's use atom w. Need to give it the parameters, learning rate. Let's do a standard learning rate. Let's say optimizer.zero grad. Zero out the gradients. We'll put it that here. Optimizer, sorry, loss.backward. Do a compute the value of the weights with respect to the loss function, and then update the weights, update the value of the weights. And then if we do that, let's just say 1,000 times, let's say 2,000 times, and then generate again, it should look better than what we got here. So let's see if this works. Yep. We can see it started to look more Shakespeare-y like, and the losses went from somewhere around ln of 65. That's a lot of, somewhere around ln of 65, which was like 4 point something. Yep, 4.3 all the way to 2.7. So yeah, our naive model is working. Okay, so let's start adding to the model, making it successively better and better. So let's add an attention head and positional embeddings, because attention is position invariant, so we'll need to add positional embeddings. We won't use sine cosine embeddings. We'll just use positional embeddings as trainable parameters, which is just easier to implement for now. I can do another video where I actually implement sine and cosine embeddings. Also, I'll do rotary embeddings as well, because those are pretty cool and interesting. So yeah, let's say import language transformer modules STM. Let's call this transformer modules. I don't know. I can't think of a better name, so we'll just stick with that for now. Import torch.nn as guys. When I'm really coding to learn, I code everything by hand. I barely copy paste anything. I always just code it out. It helps me memorize it. It's like doing katas for karate, or I don't know, jujitsu. It's like doing drills, like repping a move over and over. I found it to be super beneficial to learn things. Using code completion and also using GPT is fantastic. They're great tools. I mean, they're incredible tools, but I also think one should train their neurons with just reps. I think this is all I need. So let's define class attention head modules. Attention head def init always the same config. I'm gonna pass this config around, of course. Super. What does attention head have? It has self dot. The queries, which is a linear layer config dot and embed to head size. Let's just do attention head and multi-head attention in one go. Yeah, so we'll say head size. Keys. Query. Let's just type it out. The head size will be passed in. Here, not in the config, because when we're going to make a class multi-head attention, which is going to call this class attention head, and multi-head attention is going to define the head size, because you're going to pass in, it's going to look at token vectors of size n embed, and then depending on the number of heads, it's going to divide n embed. So if n embed is 32 and we have 4 heads, one attention head is going to be of size 8. The vector that you pass into that attention, well, you're going to pass the full vector in here, but then it's going to go through this query key and value projections and be projected into a lower dimensional space of head size. And then we're going to do some computation in all of the heads, all of the attention heads, and we're going to concatenate them back together. So we have query key value, and then we have trail. We need, because this is causal attention, so we need to mask, any token embedding can only look at token embeddings that are before it, right? So we need to mask all of the values of the tokens that can come after, and we do that using this upper triangular matrix. So torch.ones, torch.ones. No, not an embed. Yes. Context window size. Self.register. Buffer. Trail. This will register a sort of like constant, so it doesn't have to keep computing this upper register buffer is used, so it doesn't have to keep computing this upper triangular matrix every time. Trail. And it's getting hot in here. What else do we need? Queries, keys, values. We need dropout. Dropout is essentially, imagine you have a neural network with, weights, weight layer, weight layer, weight layer. Based on a probability, you can choose to zero out different nodes, which has this effect of actually making an ensemble model. Like when you actually go to do your predictions, and when you're doing a prediction, it's almost like you're taking one neural network that had certain nodes zeroed out, plus the predictions of another neural network that had certain nodes zeroed out, and you're taking the average of all those predictions, which has a regularization effect. So dropout. And I believe we call that after the softmax, p dropout, float 0.2, probably 0.1 is fine. So what does a forward pass look like, right? So this is how attention works. We're going to self.query. So self query is what information am I looking for? So for each token in X, so we, right, so X, first of all, BTD, head size. btd x dot shape, right? So batch number of tokens, which is the context window size, or up to the context window size, and d, which is the numbers, which is n embed, n underscore embed. That's the shape of the tensor coming in. So for each of the token vectors, each of the tokens in that batch, in a single batch, each of the tokens, the query computes what information am I looking for. So the weights of the query layer are values that when X is passed through it, it creates this tensor that contains information that says like, what information am I looking for? And then, okay. Keys are what information do I contain? And then the values are what information do I want to communicate during aggregation of token values. Because what we're going to do is we're going to pass X through the query. So what information am I looking for? Then pass all the tokens through the key weights. What information do I contain? And then we multiply them together. So we multiply what am I looking, so for a single token, it contains, the query contains what am I looking for, and then all the other tokens contain what do I contain, right? What information do I contain? So if what I'm looking for matches what something contains, the higher the dot product will be, right? And then that, if we do that for each token against every other token, we get this attention matrix that contains, if the information this token is looking for is similar to the information a token contains, there's a high, the number is high. And then what we do is we have this distribution of, we normalize that matrix to create a distribution, and then we pass the tokens through the value vector, which is what comes out on the other side is basically what information do I want to communicate during the aggregation of the token values, right? Because what's going to happen is we take the attention weights and we dot product it with the value, we multiply it with the value, and what that does is basically a weighted aggregation of all the tokens that came before. So like if I'm the fifth token in a sequence, by the time we get to the attention weight time the value matrix step, if I'm the fifth token in the sequence, all the tokens that came before it in the attention matrix basically have what information am I trying to communicate during this aggregation, and how important is that information? And then we sum it up together, and that equals, it's sort of a representation of the importance or non-importance of the information and the relationships of the tokens that came before that specific token. This is all stuff that I will explain in more detail when I have my iPad. So queries, keys, value. So now we do Q Q at K. So let's put this above. This is gonna be dimension B, T, D, sorry, head size, H for head size. B, T, H, B, T, H. And then, so if we want to multiply Q and K, we need to transpose H with T. So we'll do T times H times T, right? Which gives us T times T. So BTT. So 1, 2. This gives us BTT. And then we multiply that times D times the square root of D. So negative D times negative 0.5, right? To scale the attention weights so that, especially when we are initializing, when we're doing during initialization of the network, when we're doing like the first pass, the weights don't get too large. Which causes numerical instability and all types of problems during training. Can cause overfitting, all types of vanishing gradients, exploding gradients, all types of issues. So, and then attention equal. Then we do the masked fill, and we use our self.trill. It's self because we defined it as a register buffer. So this trill, what we named here, is now a property of the class, and it's constant. Self.trill. So we're going to basically, wherever self.trill equals 0, which is going to be the upper right triangular portion, we're going to give it a value of negative inf, so that when we compute soft max of ATT over the last dimension, right? Because over the T dimension, right? Softmax, the softmax of when it sees these negative inf values, it's going to go to 0, which is going to zero out any value of tokens that come in the future. And then we're going to do self.dropout on this. And then we're going to do, so this should be BTT. And then we're going to do attention at V, which should give us BTH. Or you can just say and now class multi-head attention should be module what multi-head attention does is basically splits off, creates n number of attention heads. So each attention head can it can learn different types of information from a set of tokens from your data, and then it aggregates the information into one token. So each attention head will learn different information about your text. And we do that, so we say attention heads equals module list we'll say attention head config head size, which we'll define in a second, for in range config.n heads. So let's go over here. We'll say n heads int is 4. We'll go back over here. So we'll say head size is equal to config. So right now the dimensional size of the embeddings is 32. We divide that by 4. That gives us 8. So each attention head will have a head size of 8, which means that when we pass the tokens through the query keys and values, it'll project it into a lower dimensional embedding space of size 8. And then each attention head will do some computation. It will produce these tokens that contain aggregated information from all the other tokens in the past of dimensional size 8, and then it will concatenate them all together in an embedding of size 32. So back to the original size. Module list. We actually need a projection. Well, we'll do this later because this will be for skip connections. So forward will be x receives torch.cat. Self head x for x in for head in self.attention heads. So right, we have this list that contains the resulting tensors for passing our input data x through all the attention heads. And then we're going to concatenate that on the last dimension, which is the embedding lookup dimension, right? So, and then that will give us our original token dimensions of size 32. We can test modules. Yeah, we can do that here. Class. Module multi transformer modules is TM multi-head attention fig something's off. That's why the editor isn't responding properly. Oh, right. I didn't close that parentheses. So test modules takes this config. Head size should be defined. Head size is not defined. Or sorry, end head should be defined. It is. Test modules. So let's see if this is going to get called. Oh, abort. Is required. Test modules. Must have at least 2 dimensions. So actually, this is going to be from the beginning to T. Beginning T. I think that's what it's complaining about. Line 12 of transformer modules set MU12. Torch.trill, torch.ones. Torch.trill, torch.one. Oh, right, this needs to be in a square matrix, square tensor. So, and then I also added this here so that we're saying we need to index from the beginning up to the up to T, because we can have maximum of context window size, but T can be less than the context window size. So we don't want to index outside of the outside of T, even though context window size can be greater than T. Okay, test. So we want to test multi-head attention. So in tensor, let's say torch dot zeros of size batch 4 B T D 4 8 and 32. Let's test actually attention head. So based on the value set in config, n heads is 4, so then the output should be of size 4 8. Shape should be 4 8. 32 divided by 8 is 4. Assert that out tensor equals out shape. Size equals config that. empty, received an invalid combination of arguments, got tuple, d-type, non-type. Do I need to find where is this? Transformer modules, line 8. Config and embed. Line 114. Line 8. Config. Head size. Oh. For 8. Oh yeah, it should be 8. 32 divided by 4 is 8. Okay. And then multi-head attention. Boom. Still might not be perfect, but that's a pretty good sanity check, just to make sure the shapes align with what we expect. So now, if we go to language model, now we need to add positional embeddings. We're not going to use sine cosine. We're just going to use another lookup table that contains learnable parameters, and then the lookup index. The lookup is going to be indexed by the context window size, so 0 through 7. So for the 0, if something's in the 0 position, you're going to look up the embedding, the positional embedding that's there, and add it to the token embedding. So of course, the resulting vector is going to be a size and embed. It has to match the token embedding size. And then we're going to have multi-head attention. Equals tm.multi-head attention, and we're going to go to the forward self.embedding table. We're going to say x is toke embed plus add the positional embedding as an offset, and then we're going to say x receives self.multi-head attention x, and then we're going to pass that to the language model head to get logits over our vocab size. And now, if we train that, we should see the language start to improve from where it was before. So we can remove transformer modules, multi-head attention. (164) module, torch language modeling, video 64. Position embedding table. Oh, right. We're not going to give it inputs. We're going to give it, we're going to give it literally the value 0 through 8. We're going to give it a 0 and 1, 2. We're going to say, give us the positional embedding for the 0 position. So we pass it to 0. It looks up the position at in vector at index 0. So torch a range self dot config dot context window size. I think that's it. Going through the losses again. It's really hard to track this, so actually we're going to fix that right now. 65, line 65 and forward. Line 65. Is this during generation? Line 84 and generate. Line 84. I think this thing is weird about this. We're concatenating over the last dimension, which would be, no, this isn't right. Oh, right. I know what the issue is. Torch.a range should be over t because this is going to give us out of index. It's basically going to be out of index. Inputs dot shape bt d. Language modeling 105. Line 63 and forward. Oh, right. There's no D. Boom. So we can see that mass multi-head attention is at least working. We don't know how it's working compared to what it was before. One, because we haven't been tracking this too well, but two, because I decreased the number of iterations, but also tracking the loss the way we're doing it right now, where we're printing out the loss after it computes for each mini batch is too hard to track. So we're gonna create this function called estimate loss. That's basically going to average the loss for a batch. So every 200 iterations, training iterations, we'll estimate we'll get a value for the training loss and the validation loss. So for split and now we need to model X, Y, logits, loss, So for the trainer, so his out will be a dictionary that contains the mean of the loss for 200 iterations. So first it'll compute the average train loss, and then it'll compute the average validation loss. And we'll do that every modulo enters data estimate loss, which takes model split and config. Model doesn't take split because it does both. Run that. Oh, actually, let's. So every 500 steps, we should see the loss. This is a little easier to track now. Oh, I know why it looks weird. First of all, we don't want it to store the values. We don't want it to store compute values. So at torch.nograd, and then we also want to say model. When it's computing the estimated train and validation loss, we want to put in eval, and then put it back in the train mode at the very end. Let's see. Oh, right. That's why. There you go. Now we're in business. So let's start coding some more. Let's finish out the rest of this transformer. So we need layer norm. My layer norm is going to be self-config super init self.gamma torch.ones. This is going to be the scale and the learnable parameters that can scale our normalizations by a certain value. Beta. How about we just pass in dim EPS. Let's give it the default value. This will be some noise that we add. This will be some value we add for numerical stability. Then make it 0. So initializing this to ones makes it so that in the beta to 0 makes it so that we don't scale or shift the normalizations at first. When the model initializes, it'll learn how to shift it or scale it over time if it chooses to do so. Forward self. Yep, here we go. It's learning language better. We can tell the loss is a little bit lower than it was before. I don't know if we have record of that, but I also want to change the progress. I want to use TQDM, make a progress bar to make it easier to track. Self X, so X, we're gonna, for each token embedding, we're gonna normalize each token embedding. So for the character C, we have a token embedding, and whenever we apply layered normalization, it normalizes that token embedding. So it computes the mean and the variance for each value. It treats that token embedding as a distribution and computes the mean and variance. Does 0 standardizes that token by the mean and the variance of that specific token. So we need the mean of the last dimension, and then keep the dimension shape, keep the dimensional shape, so we can do the vector operations. X equals x hat minus, right? X minus x mean. Torch.square root x plus man, it's getting so hot in this room. So hot. And then x hat, then we'll scale shift by, we'll scale by the learnable parameters. So let's see. We have layer norm. So now we're going to need that to implement we're also going to need this feed forward def init self config. We'll need this self.net equals and sequential So we're actually going to, in the original transformer paper, we project the tokens to a higher dimensional space. So 4 times config.n embed, and then activate it, add some nonlinear activation, and then project it back down into the original space. And then add dropout. It is hot in here. Forward self x return self.net x. Okay, and now we need transformer block. Transformer block. Transformer block is the transformer block is multi-head attention and then linear layer. And then it also has residual skip connection. So MHA is multi-head attention config, and then feed forward is the feed forward module I just defined, and then it also has layer norm, my layer norm, and the way it's constructed is X receives self.layerNorm1. First we normalize. We do pre-normalization, which is different from the original paper, but now all these transformer models do normalization before they do some kind of computation. And then we say X for a residual, we add the identity to, when we fork off, we do some computation, and then we add it to the identity X, which preserves the gradients. And then we normalize again before we fork off and do some computation, some projection. Self.feedForward X, and we return X. Okay. This is our transformer block. So if we were to add our transformer block here, tm.transform block. Let's see what happens. Invalid syntax. I know what it is. Zero 54 transformer modules. Zeros. Nice. And it's gotta be 87. It's gotta be like 90 degrees in this room right now. So I am just losing water, chugging away. And we're gonna add to that by drinking some caffeine. Okay, now we definitely have better language than we did before. We don't even need to look at the losses. Even I believe before it was 2.4 something, the final validation loss, but it doesn't look like it's overfitting either. Maybe a little, possibly a little bit, possibly. I can't really tell. There's some variance in between the train and the validation loss in terms of what's higher than the other. But it doesn't look like it's like super overfitting or anything. Looks like it's kind of oscillating, but yeah, it's definitely learning language better. Let's. Oh, I need to. Also, there's a projection. The original paper has a projection. Back once it does multi-head attention, it sends it through a linear layer and projects back into the original dimensional space. So we could change this. We could change the output of multi-head attention to something, and then match the dimensions here, and then project it back into the original dimensional space here if we wanted to. But we'll just add this linear layer here. Let's just run it again just to make sure. Yeah, looks like it's working fine. I want to add something. Let's see. So I grabbed some of this code right here for TQDM. I want to adapt it for our use case. So let's see. P bar progress bar equals TQDM range fig max errors. So then I think for iter and epic bar, for iter and p bar, p bar dot set post fix. this is gonna work. Nice. Yeah, this is a lot easier to track. Ay, ay, ay. So we have about one more thing to add to this transformer. I think we have everything so far. We're gonna add transformer blocks. This is language model. So instead of a single transformer block, we're gonna have n blocks, and let's just say 2 for now. And then where's language model? Blocks receives dot sequential nice, and then dot sequential transformer block for in range config dot n blocks. Right, n blocks, yes. Yes, and then we'll just apply x receives self dot blocks. So let's see what happens. Transformer block is not defined because I need to say tm. Boom. Man, it is so hot in this room right now. Let's let that train for a bit. It's working. It's working. Yeah, this is our transformer. I think I'm gonna end this video here. Where the next video is, I'm basically gonna scale the model up and deploy it to a a virtual server online. I'm gonna use OnePod. And yeah, you're gonna see how we can learn language. You're gonna see a big difference in the language that it produces. And then I'm going to make this into a word-based tokens. So I think I'll take a break here for now. Maybe I'll make a separate video, make it a separate video entirely, or I'll add on to this video, but 2.33, let's let this run for now. Let's commit this.